How do we solve this problem? In this video, we are going to look at some calculations under gravimetry analysis. So before we continue, we need to know some formulas that we'll be using in this video. Basically, we'll be looking at something known as gravimetric factor. The gravimetric factor, normally represented by GF. So the gravimetric factor is going to give us the weight of analyte, what we are looking for, and the weight of precipitate, multiplied by A on B. And A on B here is our geometric coefficient, and we will have to look for that too before we'll be able to calculate for our gravimetric factor. So that's one formula you need to know. Assuming we have NaCl, our analyte now is Cl, we have to calculate the gravimetric factor for Cl in sodium chloride. It's going to give us the weight of Cl divided by the weight of the whole of sodium chloride multiplied by the stoichiometric coefficient. So with this, our GL for chlorine is going to give us molar mass of chlorine over molar mass of sodium chloride, and this is going to give us 35.5 gram per mole, all on 58.5 gram per mole. So simplifying this gives us a gravimetric factor for analyte chlorine. What about A is to B? Well, we have to look at the coefficient of our analyte. The subscript of our analyte, chlorine here is 1. And if we see that in the precipitate, it's also 1, then there's no problem. So it's going to be 1:1. So which has no effect. Which can be, generally ignored. Assuming we have Fe to be our analyte and Fe to O3 to be our precipitate, and we have to look for the gravimetric factor in terms of our analyte Fe here. So we know that our gravimetric factor is going to give us the mass, the molar mass of the analyte, which is molar mass of Fe, all on molar mass of our precipitate, which is molar mass of Fe2O3. Now let's look at the subscript of our analyte. Our F here has a subscript 1 here, but our F here has a subscript 2. So we have to find a way of cancelling this out, or making it balanced. And what do? Because see that here F is 1, here F is 2. So we just multiply this place by 2 in order for them to be balanced. So that is it for this. You can just look for a molar mass of Fe, a molar mass of this, and then substitute in, and you're going to get your gravimetric factor. The whole thing is that, let's say if you have something, if at the bottom we have A to be 2 and B to be, let's say here A here, we have A here to be 2, A here to be 1. We just want to find a way of making A here, A at the top and A at the bottom to just balance. So we can just multiply this place by 2, or we just multiply everything by 2 on 1. So that's it for gravimetric factor. How can we determine the gravimetric factor for our analyte MgO index? So we know that our gravimetric factor is going to give us the molar mass of this, molar mass of Mg, since this is our analyte. So molar mass of NgO, or molar mass of Mg2P2O7. So now let's base on our metal aspect. Like here we have our Mg to be 1, subscript 1, and here to be 2. So we just have to multiply this by 2, so that at the end of the day we have 2 of Mg at the top and 2 of Mg at the bottom. So we are basing on our metal, our substance that will provide the cationic part. So far that's one formula you need to know, and let's proceed. One thing we can be asked to calculate is the weight of our analyte, and the relation is weight of our analyte is going to give us the mass of precipitate multiplied by our gravimetric factor. So that is another formula you need to know. And the third formula that we'll be looking at is the percentage analyte that we have in the percentage analyte calculation. So our percentage analyte percentage analyte is going to be the mass of our analyte or weight of our analyte over weight of our sample multiplied by 100%. So we'll be solving a lot of examples in this video, different examples. I mean, the questions are in different forms for us to be well equipped. In precipitating chloride from a solution of silver nitrate via addition of dilute HCl, 3.5 grams of TPT is obtained. Calculate the percentage chloride in a 6.0 gram sample. So how do we understand this question? Yeah, the things that we'll be looking for is what is our precipitate and then what is our analyte. Here we have to calculate the percentage of chloride in the sample. So directly chloride is our analyte here. Then what then is our precipitate? Our precipitate is going to be silver chloride. We are precipitating chloride from a solution of silver nitrate. In the presence of silver nitrate, definitely we are going to form a precipitate of silver chloride. So now let's go ahead. We know the weight of our sample to be WLs to be 6.0 grams. And the molar mass for AgCl is given to us here. So now that we know that our precipitate is AgCl, what is the mass of our precipitate? I mean, the mass of our precipitate, which is silver chloride, let me represent it by AgCl, is 3.5 grams. So 3.5 grams here. Now, what do we need? We have to calculate for the percentage of chloride in the sample, but we need to know the mass of chloride in the sample before we'll be able to calculate the percentage. So we then just go ahead and calculate for the weight of chloride in the sample. Percentage chloride is going to give us mass of chlorine over mass of AgCl by 100%. I mean by 100. So in this case, we don't know the weight for our chloride in the precipitate, so we just have to look for that. But we know the weight for our precipitate, which is 3.5. So let's go ahead and do that. And we know that weight or mass of our chloride is going to give us the weight for our precipitate, AgCl, multiplying our gravimetric factor. And our gravimetric factor is simply the weight of our analyte, which is chlorine, over, a whole of AgCl, the precipitate. Weight of AgCl is just 3.5. So 3.5 grams multiplied by our gravimetric factor, which is mass of chloride over molar mass of AgCl. Here, let's look at our analyte. The subscript for our analyte and the subscript of our analyte in the precipitate is just the same. So we just leave it like that. So mass of chlorine is going to give us, we are going to get something like 3.5 grams multiplied by mass of chlorine, 35.5 grams per mole, all over. Mass of AgCl is given to us here, 143.46 grams per mole. And this is going to give us 0.8661 grams. Now that we have the mass of chlorine, which is our analyte here, we can now calculate for each percentage in the precipitate. So let's go ahead and do that. So percentage chloride is going to give us mass of chloride over mass of our precipitate multiplied by 100. And this is going to give us mass of our chloride that we calculated to be 0.8661 grams, all on mass of our precipitate, which was given to us as 3. No, it shouldn't be mass of our precipitate here. It should be the mass of our sample in the solution. Our mass of the sample that we've taken. So which is WS here. So WS here. So this is going to be the weight of our sample and not our precipitate. We use the mass of our precipitate in calculating for a gravimetric factor. So let's correct that. So the weight of our sample is 6.0 grams. then multiply by 100%, and this is going to give us 14.44%. So that is for this question. An ore sample is analyzed and found to contain 5.97% manganese. What mass of the Mn3O4 PPT precipitate can be extracted in 1.50 gram sample? How do we solve this problem? In this problem, we've been given the percentage of manganese, Mn here, and we have to look at the mass of Mn3O4 precipitate that can be extracted in 1.50 gram sample. So weight of our sample here is 1.50 grams, and we have percentage of manganese given to us to be 5.97%. Now, before we can be able to calculate for the weight of Mn3O4, we have to know the weight of Mn, so we can just go ahead and use the percentage of Mn given to us to calculate for the weight of Mn. And we know the formula is, if from the point of Mn being our analyzed weight of Mn is going to give us, let's write the full expression first, the percentage formula for Mn. So percentage Mn is going to give us weight of Mn over weight of sample multiplied by 100. So now we want to look for weight of Mn here. So just go ahead and make weight of Mn the subject, and we are going to get something like weight of Mn be equal to percentage of Mn multiplying weight of our sample all on 100. So let's just substitute our values in. We are going to get percentage weight of Mn to be 5.97. So 5.97 multiplied by sample weight of sample, which is 1.50 grams, all on 100. So this is going to give us 0.08 0.808955 grams. So that's the weight for Mn. In calculating for the weight of Mn3O4, we know that weight of analyte, if Mn3O4 is our analyte now, is going to give us weight of our precipitate, which is Mn by gravimetric factor. So this is going to give us, so weight of Mn3O4 to be weight of Mn that we calculated to be 0.8955. So this is 0.8955 grams by gravimetric factor. And our gravimetric factor for MnO4 is going to give us the molar mass for Mn3O4 over molar mass of Mn. In this case, looking at the subscript of our Mn at the top here is 3, and here Mn here is 1. So we just multiply this side by 3. Go ahead and do substitution. So molar mass for MnO4 is given to us here to be 228.77. We are going to get 0.08955 multiplying, this is in grams, multiplying 228.77 grams per mole, and out of, all over, molar mass for Mn is 54.92 grams per mole, and don't forget to multiply it by 3. So this is going to give us 0.1243 grams. So this is the mass of Mn3O4 in the sample of mass 1.5 grams. Calculate the percentage of phosphorus and P2O5 if 1.268 grams of ammonium phosphomolybdate were obtained from 0.371 grams of fertilizer sample. So how do we solve this problem? First of all, we need to know what our analyte is and what we are going to look for, either the weight of our analyte or percentage composition of our analyte. So those are the basic things that we need to look out for, no matter how complex the question is. If we are able to spot out our analyte and what we have to calculate for, then it becomes simple. In this case, we are going to look out for percentage of phosphorus and P2O5 in in ammonium phosphomolybdate. So let's represent this whole compound by ammonium phosphomolybdate. So APM. Before we can calculate for the percentage of P and percentage of P2O5, we have to know their masses, their contributions in the sample. And one thing we've been given here is the weight of our sample, which is 0.371 grams. So now what we don't know is the weight of P and weight of P2O5. So let's go ahead and calculate for the weight of those analytes. And one thing we've also been given is the weight of our precipitate, which is 1.268. So weight of, going to represent this by weight of APM gives us 1.268 grams. And from our formulas, weight of our analyte is going to give us the weight of precipitate by gravimetric factor. So now let's take phosphorus. So weight of P is going to give us weight of APM, which is our ammonium phosphomolybdate here, by our gravimetric factor. And our gravimetric factor is going to be the weight of our phosphorus here, which is molar mass of our phosphorus here over molar mass of APM. In writing our gravimetric factor, we need to look out the subscript of our analyte and from the denominator and the numerator, whether it is the same. So we can see here, our analyte here has a subscript of 1, and in the whole complex, the precipitate, it also has a subscript of 1, so we are good to go. So this is going to give us weight of APM is 1.268 grams by molar mass of phosphorus is, let me check that, is 30.97 grams per mole, all on molar mass of APM, which is given, then we just have to calculate for molar mass of APM. Let me do that. The molar mass of APM must be given. So APM has a molar mass of 1858.05 grams per mole. So we're going to use that. So it's going to be 1858.05 grams per mole. And this whole is going to give us 0.0211 grams. So let's go ahead and calculate for the percentage of phosphorus. So percentage phosphorus is going to give us mass of phosphorus over mass of sample by 100. And this is going to give us weight of phosphorus is 0.0211 grams over weight of our sample given to be 0.371 grams by 100. And this is going to give us 5.69%. So that's it for this question. Let's look at our final example. In analysis of 6.0 gram sample of phosphorus, a mixture of chloride of potassium and sodium weighing 0.11 grams is obtained. Treatment with AgNO3 finished 0.2451 gram AgCl. Calculate the percentage sodium oxide and potassium oxide in the sample. So how do we go about this question? This is actually 0.6. So let's write down our parameters here. We have weight of our sample to be 0.6 grams, 0.6 grams, and we have a mixture of chlorides of potassium and sodium weighing 0.118 grams. So a mixture of chlorides of potassium and sodium weighing 0.118 grams. That means that we have sodium chloride plus potassium chloride giving out 0.118 grams. So in problems like this, we need to form equations. So this is our first step, giving us that potassium chloride plus sodium chloride gives us 118 grams. So let's look at another hint here. That treatment with AgNO3 finished 0.2451 grams AgCl. So after potassium chloride and sodium chloride giving us this, after we treat it with silver nitrate, we got the potassium chloride and sodium chloride to form AgCl again, silver chloride again, and that gives us a mass of 0.2451. So we can form two equations and then solve for the various masses of sodium chloride and potassium chloride. So firstly, we have our sodium chloride and potassium chloride giving us 0.118 grams. So let's say our X should be sodium chloride and then our Y to be potassium chloride. So we can then go ahead and say our X plus Y to give us 0.118 grams. So anytime you see a question like this, it's better you form equations and start solving. And it's very simple. The question itself will indicate the approach that you should go about. So now this is our first equation. So let's look at the other equation. We have AgCl formed from both NaCl and KCl. So what mass can we get? What mass of sodium chloride will combine with KCl to give us the a full mass of AgCl, which is 0.2451 grams. Well, if I know that a sample A and B gives me C, and I know the mass for C to be 2 grams, that means in basic calculations, I can spot out the mass of A and B that combine to give me C. So I can just say, let's say A, I know the molar mass of A and I know the molar mass of C. So I can just calculate the mass of A here by saying mass of A by molar mass of A by molar mass of the product. It will give me a certain mass that, let's say, 1.5. And when I'm done to, I can also get the mass for B by saying mass of B over molar mass of B to give me, multiply by the molar mass of our product to give me something like 0.5 grams. So at the end of the day, if I add this and this, I should be getting my 2 grams, which is the mass of the product. So let's apply this formula in our calculations. So we know that mass of our sodium chloride, a certain mass of sodium chloride combined with a certain mass of potassium chloride to give us a full mass of AgCl, which is here. I mean, let's say X plus Y2, giving us a full mass of AgCl, which is 0.2451 grams. So how do we spot the mass of this if we know this? So mass of sodium chloride in grams over molar mass of sodium chloride. The molar mass for sodium chloride is 58.44 grams per mole plus mass of a certain mass of Y over molar mass of Y. We know Y to be KCl. So molar mass for KCl is 74.55 grams per mole. But we are to multiply each term here by the mass of AgCl, which is 143.32. And here too, it should be the same, 143.32. So just like this. Let me write everything again. 0.55 grams per mole multiplied by molar mass of AgCl, which is 143.32 grams per mole. It should be equal to, the whole of this will give us the mass of AgCl that we obtained, which is 0.2451. So you see, we multiply each term, like this is our X and molar mass of X, multiplying the molar mass of the product, and this is our Y, or molar mass of Y, multiplying the molar mass of the product we got, then it's going to give us a certain mass of X and a certain mass of Y. When we combine, we get a total mass that was produced. So in this case, when we simplify this, we are going to get 2 point, let me change this. We are going to get 2.4524x, and then plus 1.9225y, giving us 0.2451 grams. So this is our second equation, and we already got our first equation to be y plus x, giving us 0.118 grams. So the question that you want to ask yourself is that why is it that we did not use the principle that we used for the second example? Mass of X over molar mass of X multiplied by molar mass of the product that we got, because this was giving us, it was given to us in straightforward, like a mixture of chloride of potassium and sodium weighing this. That means we mixed chloride of sodium and potassium going to give us this. So there's no need to use this principle. This method to get masses over there again. So even when we use that, we will not even get the mass straightforward. We still got something like X to solve. So now let's go ahead and solve this equation simultaneously. So in order not to make this video lengthy, so let's use a calculator and solve these two equations simultaneously. First of all, we have to make sure that the equations are arranged in order. Let's say if x will come first, then and y will follow in the second equation. It should be the same for the other one. So here we have x and x, here we have y and y, giving us something. So let's go ahead and put our values in the calculator. So mode 5 1. So first value for x, we are going to key in the equations one after the other. So first value for x is 2.4524. So first equal to second value for and the first value for y is 1.9225, then equal to what we got, which is 0.2451, then equal to, you see, we start from the second equation. First, in the first equation, we key in the coefficient of x followed by y. So we have to do the same for the second equation. So 1 equal, and then 1 equal what, 0.118, then equal. So this is going to give our x to be, so now our x, sorry, to be 0.0344 grams, and pressing equal to, again, gives out the value for y, and then y equal 0.0836 grams. So now let's look at the question again. What are we even to calculate here? That we should calculate the percentage sodium, sodium oxide and potassium oxide in the sample. So we are doing all these calculations to know the amount of sodium chloride that is there and potassium chloride that is there. Then we can go ahead and use our potassium sodium oxide as an analyte again and potassium oxide as an analyte again and calculate its percentage since we know the masses for sodium chloride and potassium chloride. So let's go ahead and do that. So our interest is to look for potassium oxide and sodium oxide percentage. So before we can calculate for the percentage of potassium oxide or sodium oxide, we need to know its mass. Then we therefore use the mass of the whole sample to calculate the percentage. So now we now know our the mass for sodium hydroxide, which is mass of sodium chloride, which is X, and mass of potassium chloride, which is Y. So now with reference to this, let's look for mass of K2O from this. So it's going to give us mass of our precipitate, which is sodium chloride, grams of sodium chloride, multiplied by a gravimetric factor. And then gravimetric factor is going to be the molar mass of K2O over molar mass of sodium chloride. Since we are referring to sodium, this will be potassium chloride. So going to be molar mass for potassium chloride. So wait for K2. And we know the mass of potassium chloride to be 0.08. So 0.0836 grams by molar mass for K2O is going to give us 94.20 grams per mole. All on molar mass for KCl is 74.55 grams per mole. And this is going to give us 0.0528 grams. We have to look at we have to calculate for the percentage of potassium oxide and sodium oxide. So now that we know the mass for potassium oxide, we can go ahead and calculate its percentage. So this is the weight for potassium oxide, and percentage K2O is going to give us weight of K2O over weight of sample by 100, and weight of our sample is giving us to be 0.6 grams, and we know our K2O to be 0.0528 grams, all on 0.6 grams by 100, and this is going to give us 8.78%. So that's it. The first part, that's it for K2O. That's the percentage of K2O. And now we are going to calculate for the percentage of Na2O. We got the mass of sodium chloride, sorry, 0.0344 grams. Then we can go ahead and use this for. So now we are going to use, we know the weight for Na2O, weight of Na2O to give us grams of NaCl by gravimetric factor, which is going to be molar mass of Na Let me use this. So weight of any 2O is going to give us the mass of NaCl by the gravimetric factor of Na2O, which is the molar mass of Na2O over molar mass of sodium chloride, which is NaCl. So now here, you see that we have to multiply this side by 2 because our N here has a subscript of 2. So we just have to multiply the denominator by 2 in order to balance it. So molar mass of sodium chloride is 0. From here, we calculated here, 0.03, let me write this here, 0.0344 grams by the molar mass of Na2O is 61.98 grams per mole, and the molar mass for sodium chloride is 58.44 grams per mole, and the whole of this is going to give us 0.0182 grams. Now that we have the weight for Na2O, we can go ahead and calculate its percentage. So percentage Na2O is going to give us weight of Na2O over weight of sample, which is 6 by 100%. So weight of Na2 is 0.0182 grams all over 0.6 by 100. And this is going to give us a percentage of 3.03. So that's it for this question. So that's it for this video. In next video, we'll continue our calculations with a lot of examples too. So kindly subscribe to my channel for more videos like this. Bye.